design. The main components of the crescent pump include the housing with a crescent seal and ports, the end cover, the input shaft, the drive gear, which is an external gear, and the ring gear, which is an internal gear. The drive gear, which has fewer teeth than the ring gear, sits offset in the ring gear. This creates an open cavity between the two gears. The crescent seal, which is machined into the housing, divides this cavity, creating a positive seal between the inlet and the outlet side of the pump. The input shaft turns the drive gear, which drives the ring gear. As the teeth unmesh near the inlet, atmospheric pressure pushes the fluid into the pump inlet. The fluid flows through a kidney-shaped opening in the housing into the cavity between the gears. The two gears move the fluid across the cavity, past the crescent seal, to the high-pressure side. As the gears mesh near the outlet, the fluid is forced out the other kidney-shaped opening to the outlet. A gerotor pump is an internal gear design. The main components of the gerotor pump include the outer gerotor element, which is an internal gear, the rotor or internal gerotor element, which is an external gear, the input shaft, and the housing with the ports. The rotor, which has one less tooth than the outer gerotor element, sits offset in the outer element. This creates an opening cavity between the two gears. The two opposing teeth divide this cavity, creating a positive seal between the inlet and the outlet. The input shaft turns the rotor, which drives the outer gerotor element. As the teeth unmesh near the inlet, atmospheric pressure pushes the fluid into the pump inlet. The fluid flows through a kidney-shaped opening in the end cover to the cavity between the gears. The two gears move the fluid across the cavity, past the opposing teeth, to the high-pressure side. As the gears mesh near the outlet, the fluid is forced out the other kidney-shaped opening to the outlet. A variable displacement pressure-compensated pump is designed to respond to pressure changes that occur in a hydraulic system. There are several advantages of a pressure-compensated circuit: energy conservation, better controllability, and concurrent actuation of several circuit functions. Some of these advantages may be offset as a result of higher component costs. A variable displacement pressure-compensated pump is most often used in a closed-centered system. In this example, we've used a pressure-compensated pump. It is helpful to understand the functionality of a piston pump. If you need to review this, return to the Pumps menu and go to the animation for piston pump. In this example, when the control valve is in the center or closed position, the pressure forces the compensator spool to shift up against the spring setting, allowing the pressurized fluid to shift the control piston and the swash plate to a vertical position. When the swash plate is vertical, the pump is now at zero stroke or no flow, and the pressure at the outlet port is maintained at the set pressure. A very slight amount of flow is produced to lubricate the pump and maintain compensated pressure. This flow is vented through the pump case drain port. When a circuit is actuated and the pump control senses a pressure drop, the spool shifts away from the spring and fluid is vented from the control chamber into the case of the pump, and the swash plate rotates on stroke to produce the pressure and flow required by the actuator. Of the three types of hydraulic pumps discussed, gear, vane, and axial piston, only the vane and piston may be pressure compensated.
The term hydrostatic, as it refers to hydraulic circuits, is any circuit using a pump in combination with a hydraulic motor. In this section, you'll learn the difference between an open circuit and a closed circuit, the purpose of the components used in these circuits, and the basis of operation of hydrostatic circuits.
In an open circuit, hydraulic fluid supplied to the pump inlet comes from the reservoir and is returned from the actuator back to the reservoir. In most open circuits, hydraulic fluid is fed to the actuator by a directional control valve and returned to the reservoir in the same way. This first circuit is a basic system with a hydraulic pump and a hydraulic motor. When the pump is in operation, flow is directed to the hydraulic motor, causing the motor to rotate. If the pump is not rotating, the hydraulic motor will not turn. In this circuit, a directional control valve is added to the circuit, and a bidirectional hydraulic motor replaces the hydraulic motor. The directional control valve will allow the hydraulic motor to reverse direction when shifted. This circuit adds an adjustable flow control valve and a pressure relief valve. The flow control valve allows for variable output speeds from the hydraulic motor. The pressure relief valve protects the system from overpressurization and will shift as the system pressure increases due to flow restriction in the flow control valve. In this circuit, a variable pump has replaced the fixed pump. The flow control valve is removed, an open center directional control valve is added, and a filter and heat exchanger are added to the return line. The directional control valve allows for forward or reverse direction of the motor and freewheeling of the hydraulic motor when the valve is centered. The filter and heat exchanger will condition the fluid before it returns to the reservoir. The variable pump will now allow for variable output speeds from the hydraulic motor. If the hydraulic motor rotation is restricted or stopped, the high pressure relief valve opens, protecting the system from overpressurization.